Hello and welcome to today's virtual seminar on water activity and the quality of confectionery products. Today I hope to be able to explain additional information about how water activity can be helpful when making confectionery products specific to those confectionery products. And this is part of a group of virtual seminars where we try to focus in on specific applications and provide information that are very detailed for that particular application. And so today this is for confectionery products. And what I want to do to start out with is just do a quick review of what water activity is. Hopefully there's the expectation that you have a basic understanding of water activity already. If you don't, I would encourage you to go to our website and watch Water Activity 101, which is an introduction to water activity. But just real briefly, the correct definition for water activity is that it is the energy status of water in a system. And we use this definition to avoid the confusion that can come from using terms like free and bound. And even though those terms still get used with water activity very frequently, the problem is that they don't have any scientific meaning, and so they mean different things in different situations or to different people. And so we try to avoid using those terms, and instead we talk about energy when we're talking about water activity. And in fact, water activity is derived from fundamental thermodynamics that tells us if we want to know the energy of water, what we need to know is how readily does it escape into the vapor phase when you put a sample in a sealed chamber. And so what water activity ends up being is the vapor pressure or the partial pressure above a sample divided by the saturated vapor pressure at that same temperature. And so if we can figure out what the partial pressure is above a sample, that gives us an idea of how readily the water in that sample can escape into the vapor phase. Compare that to the saturated vapor pressure, and we get a water activity, which is a ratio of how much energy the water in that system has in comparison to what it would have if you were dealing with pure water. So that's our correct definition for water activity. It so happens that equilibrium relative humidity is the same thing as water activity. One is reported as a percentage and the other is reported as a decimal. So if you had equilibrium relative humidity to get to water activity, all you got to do is just divide by 100. And so to further or give an additional example of how we define water activity and how it's measured, if you imagine that you were to take a material and put it inside of a sealed chamber, could be food, could be pharmaceutical, could be a confectionery product. Doesn't matter. Whatever you put in there, and then you allow it to come to equilibrium over time, there will be a certain amount or number of water molecules whose energy is sufficient enough for it to escape into the vapor phase. And then it will exert a pressure while it's in that vapor phase. If you allow it to come to equilibrium, which means not that that water molecules stay in one spot, but that there is no net change in the number of water molecules that are in the vapor state at any point in time. So 1 out equals 1 in. At that point in time, if you're able to measure the vapor pressure inside of that chamber being exerted by the vapor that's escaping from the food sample, that would be the partial pressure or the numerator for our water activity. If we were then to take that chamber but place pure water in there, then a vapor pressure would also exist above that water, but in this case we call that the saturated vapor pressure or the vapor pressure of pure water. And that vapor pressure is completely dictated by the temperature at which you're making the measurement. So if you know that temperature, you can know the saturated vapor pressure. So with those two values, the partial pressure and the saturated vapor pressure, we divide the partial pressure by the saturated pressure, and that gives us water activity, all constant temperature and pressure. And so a water activity, say of 0.2, versus a water activity of 0.5, the sample with a water activity of 0.2 has a lower energy, or the water has a lower energy than the sample who has a water activity of 0.5. And just real briefly then, if we compare water activity to another common moisture measurement, moisture content, and we compare and contrast those, while moisture content is a quantitative amount of water in a sample, the water activity is a qualitative measure of the energy or the energy status of water. So while moisture content tells you how much water is present, it doesn't necessarily tell you anything about the water or what it's doing. Water activity, on the other hand, provides information about its energy. How readily is it available for things to happen in the system, as opposed to just offering how much water is present. So those are two different measurements. They are related to each other through something called the moisture absorption isotherm. But they are very different measurements, and they don't tell or provide the same information or the same correlations when we talk about safety and quality of products. So looking at that relationship between water activity and moisture content, we call this again a moisture absorption isotherm. Isotherm meaning one temperature, because this relationship between water activity and moisture content will change as temperature changes. It's also very unique to each type of product or material. And the amount of water or the moisture content that exists at any given water activity is very dependent on what is the product is made up of. What is its matrix? The more sugar and polar materials that you have present in a product, the more moisture that can be held at a given water activity, or vice versa, at a given moisture content, the more of those types of materials you have, the lower the water activity will be at that particular moisture content. So these moisture absorption isotherms, as we're going to see today, are very helpful in providing information about how different products respond to gains or loss of moisture. So why is it important to measure water activity of food, of any type of food product? And the most common response to this question will be to make sure that it's safe. If most people who, if they've heard of water activity, will have heard of it because it controls microbial growth. That's what it's sort of known for. And this has been known since the 50s, that water activity can, lowering the water activity can prevent a microorganism from growing and reproducing to high enough levels that it can cause an infection. So by having a low enough water activity, you can prevent the spoilage of food over time. Now, if we take a look at where these cutoffs are, we can group them by organism. You can see here that all of the bacteria stop at 0.86, the pathogenic bacteria. So this is the reason why water activity is known as a control for microbial growth. It's also why it's incorporated into government regulations for defining potentially hazardous foods and as a preventative measure for the growth of microorganisms. So if you process a product to water activities lower than 0.86, there's no chance that pathogenic bacteria are going to grow. Doesn't necessarily mean they're absent or gone, it just means that they won't grow to high enough levels to cause an infection. And then yeast you can see at 0.88, and then the molds can get all the way down to 0.7. Most molds, there are a few osmophilic yeast and xerophilic molds that can grow between 0.7 and 0.6, and then below 0.6 is the absolute minimum for growth of any microorganism. Again, that doesn't mean they aren't present at those low water activities, and many of the microorganisms can actually survive quite well at low water activity. Survive, but not reproduce or be actively growing, in which case if you were to eat that product, you wouldn't get sick from it. But it's still present in there. This is not a kill step. So how does water activity work in terms of controlling microbial growth? Well, real quick, if we just use an example here. So the circle that you see on the image represents a microorganism, very crude drawing of a microorganism. It's basically just a membrane that surrounds a sac of solute. Water, or the solute that's in there, is going to have a combined water activity of some value. And what it relies on is having a lower water activity than the surroundings that it's in, so that water will actively move from higher water activity to lower water activity, because we know that water moves from high energy to low energy, hence higher water activity to lower water activity. If that microorganism were to encounter conditions or an environment where the water activity was lower than its internal water activity, then that's called osmotic stress. And it has to respond to that, because now it's not going to be able to get the water that it needs for its life cycles or its metabolism. It's not going to be able to access that. So as a consequence, it either stops growing or it has to try and do some sort of an adaptation to be able to handle that stress. And each microorganism has its own unique ability to be able to adapt to those conditions. Some can get to very low water activities and still access the water. Hence, you have the different growth limits in terms of water activity for different microorganisms. And they'll do this by concentrating solutes, either from its surroundings or by ones that it produces itself, to lower the water activity by concentrating the solutes inside of inside the membrane, and trying to lower the water activity. Now, it can only do this to a certain extent, as we talked about, and once it encounters water activities less than that, then it will go dormant and it will stop growing. And so that's how water activity can control microbial growth. But the question is, does microbial spoilage typically end the shelf life of confections? And the answer to that is probably no. Many of the typical confection types of products, sweets that you would encounter, are going to have water activities well below even that 0.6 level where microbial growth stops. Now, there certainly are exceptions to that where microbial growth could be and is a very important determination for the shelf life of a confection product, in which case water activity, of course, plays an important role, as we've just discussed. But we want to talk a little bit more about some additional ways that water activity can be useful in terms of shelf life that maybe aren't necessarily associated with microbial spoilage. If that's not what the problem is that ends shelf life, then there's no reason to try and track that or trying to look for correlations to water activity. Something else is probably ending that shelf life. And what will that be? What else besides microbial growth and spoilage would end shelf life? And there's several different types, and here's some examples, and maybe they apply to whatever kind of product that you produce at your facility. It could be loss of texture. Most confections have an expected texture associated with them, and if they don't have that texture, a consumer who goes to consume that product and it has the wrong kind of texture is going to reject that product and not want to eat it, and then they're rejected in the future. So loss of texture could be one thing that ends shelf life. Could be chemical degradation, where reactions that are not supposed to occur are occurring and causing there to be off odors or off flavors or breakdown of nutrients that could all lead to a loss of shelf life for that particular product. It could be temperature abuse. If the confection product were to experience high temperature conditions at some point during its storage or during transport, there's the possibility that that could be responsible for the end of shelf life. Could be moisture migration. If unexpected migration of moisture between different components occurs, that certainly can lead to changes that aren't expected and result in a loss in shelf life. And it may be packaging failure. It gets exposed to high humidity conditions. Packaging doesn't perform the way it's supposed to. The water activity of the product goes up, and that ends shelf life. And what you see to the right here is what we call a stability diagram. And this highlights all those types of things that water activity is associated. And in fact, water activity ends up being very well correlated to all of these different potential enders of shelf life, be it loss of texture, chemical degradation. As water activity increases, in general, the rates of these degradative reactions or occurrences will increase. Now, they do go through maximums, and they do that at different water activities depending on what it is that you're actually looking at. But in general, you're going to have good correlations between water activity and any of these potential problems that could end shelf life. And so let's go through and talk about each one individually. Now, if you want to know and determine shelf life and do some predictions, develop predictive models to try and predict the shelf life based on the conditions that your product may encounter without having put them through every type of potential conditions that they might experience, then you might use a shelf life model to do that. Now, the problem with shelf life models up to this point is that they're very focused on temperature. And this is also related to doing accelerated shelf life testing, where you put them at elevated conditions. Typically, you would put them at elevated temperatures and water activities or humidities, but the shelf life models that are available are typically based on the Arrhenius equation and just deal with temperature. And that's a problem because you need to know temperature in order to determine shelf life, but you also need to know water activity and what's happening with the water in order to get the complete picture of what's impacting shelf life. You also need to know time, obviously, and be able to know what time you're going to have under any specific conditions. And then, of course, you need to know what the product change is that occurs that ends your shelf life. Identify that, and then hopefully even find a way to quantify it so that you can track it and create some experimental data. And then you take all this information, and the good news is that we are in development and have developed a model, what we call hygrothermal time, that actually combines both water activity and temperature in order to give a prediction of shelf life based upon both of those factors. And this, again, isn't available currently, but it's something that we are in development of and have had great results for. So the question, thinking back to those potential enders of shelf life, the first one was texture. And so the question would arise, what does water activity have to do with the texture? In this case, for an example of a confection, Laffy Taffy. So this is a typical type of taffy-based confection, very chewable when you open it up. But of course, you don't want it to be too chewy or too hard, and you don't want it to be too soft so that it just sort of melts or is sticky. And so what we did is that we did a little study where we held different Laffy Taffy samples at different water activities, and you can see those represented here from 0.43 up to 0.65 water activity. Allowed them to come to equilibrium to those conditions, and then observed what had happened to them. And what we did is we measured texture on those using a texture analyzer and measured its resistance to being bent through a 3-point bend test. And so what you see reported here is the hardness that's in grams reported back from the texture analyzer. Notice that as the water activity gets lower, now natively this product is at about 0.55 water activity. Notice as it gets to lower water activities that there's an increase in that resistance. In other words, the taffy becomes harder. And then somebody was to consume that if the water activity had dropped too low, keeping in mind that most ambient relative humidities are about 30 to 40%. So if this is exposed to room humidities for an extended amount of time, its water activity is going to drop to those levels. And you'll notice that there's a drastic increase in the hardness of the taffy, in which case somebody's going to open that package up and try to bite into it, and it's going to be extremely hard, and they're not going to enjoy that product. So that would essentially end the shelf life of this particular product. Now at the upper end, we don't see quite as drastic a change of hardness, but we are able to see that it starts to become sticky on the surface, and it certainly does become softer. And it would be so soft that again, that would be an unexpected texture for this product, and hence the shelf life would end because of exposure to higher humidities or higher water activities. So at the bottom end, the product ends up being too hard. Right in the middle, where its water activity typically is that ideal range or the good. And then we have too soft and sticky at the high ends. So what you'll notice from this figure or this image is that there is a sweet spot, if you will, for the water activity of this particular product. If you move out of that sweet spot, you're going to have problems. If you go too high, there's problems of water in terms of water activity. And if you go too low, there's going to be problems in terms of the texture because of water activity. So it is important to know where that sweet spot is, be able to then identify that water activity, include that as a specification for your production, and then make sure that it stays at that water activity when exposed to other conditions by using correct packaging. So again, this is something related not to microbial growth, but to texture, and we're doing it based upon water activity, where we can directly correlate that to the water activity and even find a sweet spot in terms of water activity that very clearly would become the specification for that particular product. And if we take a look at the moisture absorption isotherm, it provides us pretty good information about why we're seeing these changes. So the moisture absorption curve is quite flat initially for this particular product, and then it starts to gain moisture at water activities above about 0.6. So at low water activities, or at the mid water activity range where this particular product would typically be, you can see that the texture is in that sort of ideal about 400 or 300 grams of resistance, which is where it needs to be in order to have the proper texture. But as you move to lower water activities, you get drastic changes in that texture. Even though you're not experiencing drastic changes in moisture content, you are experiencing big changes in water activity for small changes in moisture, and subsequently you're experiencing large increases in the hardness of that product. If you go to the other end and start sorbing water, that you can see that the taffy starts to absorb large amounts of water for small changes in water activity, and we don't get as big a change in texture, but now the product starts to dissolve and become sticky, especially on the surface. So the moisture absorption is showing us exactly why that is. On the high end, it's because it's taking up moisture and changing its moisture content, making it sticky. On the low end, the water activity is changing even though the moisture content is, and then the result of that is lower water mobility and an increase in the texture or the resistance of that material. If we look at another typical confection product, a lifesaver, we can, again, measure its moisture absorption properties and then hold it at different water activities along that moisture absorption range. And what we found, this product is naturally at about 0.2 water activity when it's processed and comes out of the package. But if it gets exposed to different conditions, then it will change. And notice again that in that range, this is quite a flat isotherm for small changes in moisture, big changes in water activity. And what we see is that as this product starts to wet up, if it gets exposed to room humidities at 30 to 40%, the surface immediately starts to become sticky, and you even get a cloudy appearance in the color. And this is where you're not taking up huge amounts of moisture, you're just changing water activity. So a lot of that is on the surface and not into the interior of the product. And as you move further up, then you start to see dissolution, where it actually starts to melt, or due to water, where you start to get breakdown of the outer portion of the confection. And if you continue to go to higher water activities, now you can see it's taking up large amounts of moisture. For small changes in water activities become quite hygroscopic, and in that case, what you'll experience if you go to high enough water activities is that the product will be completely dissolved. And all this, again, due to just moisture uptake. This is all at one temperature this is happening, and it's just due to moisture absorption. And so the moisture absorption curve clearly shows why this is happening with this particular product. So not only is the water activity helpful, because now you know you need to keep it below or close to that 0.2 water activity as much as possible, but also the moisture absorption is really providing the information that we need as well as to why this product does what it does and where it's going to really start to have problems. And here's just a quick summary or survey of water activities of different types of products matched up with their moisture contents. Notice that in general, and this is what would be expected, that as the water activity goes down, so does the moisture content, just simply because there is that relationship. But again, it's unique to each type of product. It's not a straight linear relationship across these products, because each one's going to have its own unique properties in terms of how much water can be held at a given water activity. And there are certain areas where we see distinct differences, such as for the red twists, where the water activity is lower than or just slightly higher than the other licorice product, but the moisture content is significantly higher in that particular product. And that's interesting because they're able to keep more moisture in that product, but still maintain a lower water activity, or a desirable water activity, in this case lower than 0.7, which means that product won't be susceptible to mold, but has a more moist texture to it, and plus selling water in this case as a very cheap ingredient. So very good, a very interesting relationship here for these different types of confections and for their water activities. Notice that the highest water activities are found in certain kinds of gummy treats, and then we see some of the licorice types of products in that 0.6 to 0.7 range, along with fruit snacks of different types, and then you have some gummy treats that are more down in the 0.6 to 0.5 range, and then of course the lifesavers being the lowest water activity down close to between 0.2 and 0.3. Now, so we've talked about texture, and that's one thing that can end shelf life. Another is the occurrence that could end shelf life is chemical degradation or chemical reactions that lead to the production of off flavors, off colors, off odors, all of which will end shelf life. And so there's different types of reactions that could potentially occur, such as browning reactions, lipid oxidation leading to rancidity, hydrolysis of nutrients or different materials, degradation of vitamins, enzymatic reactions that are maybe supposed to occur or not occur will be correlated to water activity. And then the stability of enzymes. If enzymes are supposed to be present and have their activity at a certain point, they have to remain stable, and that is very water activity dependent. So all these factors could play a role in what determines the end of shelf life, and all correlated to water activity. So how do you track these chemical reactions? If this is what actually is the thing that's causing problems, how do you go about finding that sweet spot that we identified for the texture? And we were able to identify it because you got lower, it was bad, and you got higher, it was bad. Well, where is the sweet spot for these chemical reactions? And in reality, the monolayer value, which you can determine from the isotherm, is supposed to represent the most stable state for any kind of material. And reactions are at their minimum. But they will increase at levels below that, especially lipid oxidation, and they will increase at water activities higher than that monolayer value. So it would be important to be able to find sort of where the sweet spot is in terms of these chemical reactions, and then still be able to make an effective or desirable product, because you can't make everything to the monolayer value. Everything would be the same, and there wouldn't be any kind of variety. So certainly it's very likely that you're not going to process to the monolayer value, but you need to know the water activity where you're going to get the optimal shelf life, or the shelf life that you're looking for, and prevent those chemical reaction rates to being too high of a level to where they end shelf life prior to what the target date is for that particular product. So how do you track these chemical reactions? Well, first of all, as we said earlier, you must account for both temperature and water activity. And it's best to, of course, use data that's collected on your specific product and not try to use standard systems and relate it to your product. You need to have some way of being able to track the progress of this reaction that may be occurring, either as the formation of one of the products or the loss of one of the reactants, whatever that might be. And then you're going to create an empirical model that accounts for both temperature and water activity. The sort of traditional or previous way of doing this was using what's called a Q10 and a QA, but it was difficult. Those two values are, the Q10 is an Arrhenius-based value. The QA was just basically taking those principles and applying them to water activity. But it's difficult to then combine them into one model that's based on first principles. So I'm going to show you how you would do it and be able to use this new thing called hygrothermal time. So in this example, we took baby formula, held it at 3 temperatures and 3 water activities, and then tracked lipid oxidation using the T-bar method, where a T-bar value greater than 1 milligram of the malonide per kilogram sample considered unacceptable. We found that this reaction follows a pseudo-zero order in terms of its kinetics, and so we could determine the reaction rate by plotting the temperature and water activity. We can determine what the reaction rate is by plotting the T-bar value versus time. So to derive this hygrothermal time model that we've been discussing, what you do is in the derivation of this, we started with the fundamental decay equation, where you can use this equation to track the progress of any reaction where you have a logarithmic relationship between rate and some other parameter that you're tracking, in this case temperature. So when we have that relationship, we can then base our derivation off of that decay equation, which is where Arrhenius is derived from as well. But if we then through substitution and rearrangement, we can get the third equation that you see up there, where we're now relating the original equation to some constants that we've placed in there. The next step is then to plot this term 1 over A, natural log of R0 versus water activity. And when we do that, because there's this correlation between water activity and reaction rate, we can actually come up with a linear equation where we can replace that value or that term with the slope times water activity minus the y-intercept, or the C constant value. And when we plug those back into the equation, we now have a rate equation that can be determined based upon water activity and temperature, and then 3 constants, A, B, and C, that we can derive then through empirical modeling to make them be the correct value in order to predict the reaction rate based upon water activity and temperature. And so we did that process with this data that was collected for lipid oxidation of baby formula. And you can see where those coefficients came out during that modeling process. So we figured out the values for A, B, and C that gave the best agreement between predicted values and actual values. And you can see that agreement plotted here as predicted rate versus measured rate, and an R-squared of 0.95. So it represents an excellent relationship or agreement between predicted and measured rates. So now with that in hand, we can use this term or this model, hygrothermal time model, hygrothermal meaning it contains both water activity and temperature, to then figure out what the rate of reaction is going to be, and thereby the shelf life, since we know as soon as we reach a value of 1 for the T-bar, then the shelf life has ended. So we can figure out how long it's going to take to get to that value under any temperature and water activity conditions. And we can even, if we're talking about discrete time periods at each of those water activity and temperature conditions, they're cumulative, where we can add them together and see how close it gets to that 1 value, and knowing that as soon as it reaches 1 in terms of its T-bar, then shelf life is over. So we can even do a real-time shelf life determination with this. So that's chemical reactions. What else could cause shelf life to end? And so the question may be, what does water activity have to do with temperature abuse? Well, water activity is temperature dependent, and at a given moisture content, the water activity will generally go up as temperature increases. So the problem here is that you could be safe at 25 degrees, but what happens at 40 degrees? And you may move to a water activity, even though your moisture content hasn't changed, you may move to a water activity that's now higher than the growth limit for microorganisms, or high enough that the texture has been affected. And so it's important to have an understanding of how water activity relates to temperature, which is unique to each type of material or product type. And so you'd want to investigate that for each of those materials. And again, this is very easy to do if you've got the ability to run a moisture absorption isotherm. You just run it at, say, 3 different temperatures, and now you know what that relationship is between water activity and moisture content at each of those different temperatures, and can account for the changes that may occur due to it experiencing temperature abuse. What does water activity have to do with moisture migration? Well, as we said, moisture migration is completely controlled by water activity. Water moves from high water activity to low water activity. If you put 2 components, in this example, say a chocolate coating with a cream filling, and the 2 are at different water activities, the chocolate may be a low water activity while the cream filling is a higher water activity. If those are placed together, they will exchange moisture until they come to the same water activity. If you want to know what that water activity is, it is possible to model that and do some calculations if you know the isotherm, moisture absorption isotherms, as shown here for each one of the ingredients. You can actually calculate what that equilibrium water activity will be. And then using additional information from an isotherm on the kinetics of that process, you can figure out just how long it's going to take to get from that initial water activity to the equilibrium water activity, where they will come to equilibrium. So all that is possible to model and know exactly what's going to happen as a result of moisture migration. What about packaging? What does water activity have to do with packaging? Well, the point or the purpose of packaging, for the most part, is to serve as a moisture barrier. It does have, of course, other purposes, but one of its main purposes is to be a moisture barrier, so that when your product is placed in humidity conditions that are different from its water activity, that there will be very limited or little exchange of moisture between the product and the surroundings. And so you're looking for a packaging material that has a very good moisture barrier. But of course, as the moisture barrier properties of a packaging product increases, so does typically the price of that product. And so you don't want to overpackage, because then you're spending money on or wasting money on packaging that's not necessary. And it ends up that you can, using water activity and moisture absorption isotherm information, it's possible using models that are based upon Fick's law of permeation or permeability, to be able to figure out exactly the water vapor transmission rate that you're going to need for a packaging to achieve the desired shelf life and prevent the change of water activity to levels that are not going to be acceptable. And this can all be done, again, through this modeling technique. Now, I've talked quite a bit about examples of doing these different types of modeling, hygrothermal time, and we offer that as a tool to be able to do those calculations. Right now, it's Excel-based, and we do offer that at no cost, but it's not very user-friendly, of course, because it's still in Excel. But we are in the process of developing a software program that will be user-friendly, that you'll be able to purchase in the very near future. We'll do all of these models and do it in a very easy interface to be able to get these calculations and do this type of modeling. Very powerful piece of software. So how do you measure water activity then? We've talked about what it impacts in terms of confection products. Now, if you're going to actually choose to measure it, how do you measure it? The most accurate way of measuring water activity is the chilled mirror dew point method. at 0.003 accuracy. It's very fast, less than 5 minutes for most typical confection products. Has a high range of water activity, and it's very reliable. It just needs to be kept clean in order for it to process. And you do want to avoid certain volatiles like ethanol in high concentrations, in which case you have to use a different sensor. We do offer a solution for that. And if you're interested in finding out more about that, just contact us. So this is the Aqualab Series 4 TE instrument. This is our top-of-the-line benchtop instrument. As we said, very fast. Has an easy-to-use interface, has onboard storage to store our data that can then be downloaded to a computer. It is got a clamshell design, so it's easy to clean and access all of the important parts. Put your sample in, close the lid, push the lever, and you're measuring water activity. Less than 5 minutes later, the value appears on the screen. So very easy to measure water activity, very easy to incorporate as part of a QA plan. Put it into a QA lab and put samples through it. Measuring water activity and making sure that you meet those requirements. Again, to be able to identify those specifications, need to do the work that we've just talked about. And in order to do that, you're most typically or likely going to need the moisture absorption isotherm. So how do you measure the moisture absorption isotherm? Traditionally, this was done using a desiccator static method where you'd put the sample in different chambers and equilibrate it to different water activities. But that process was very labor intensive and took a long time. So it was automated through what's called the DVS static method, which is uses instrumentation to do all of that automatically. And then we also have what's called the DDI, or dynamic method for moisture absorption. And that's a method that's patented by Decagon. Where we expose the sample to wet or dry air and then track and directly measure water activity and weight changes as that process happens. And if you want to know more about that, we have lots of information available on our webpage. If we compare the different methods, for most types of products or many types of products, if you do these different types of methods, DVS, desiccator, and DDI, they actually agree very well and have very good agreement. But there are some types of products where the DDI is quite different from the traditional or the static method. And in this case, this is spray-dried milk powder, and you see that there is a very distinct change or inflection in the curve as seen by the DDI method that can't be seen with the traditional methods. And this is where the DDI method really shows its colors because it has very high data resolution. You can see these sharp inflections that indicate an area that is of concern for that particular product. Now, how do you actually measure this in terms of instrumentation? Well, we have a very nice instrument that will do this called the Aqualab Vapor Absorption Analyzer. What's nice about this instrument is that it's the only instrument that actually offers doing the traditional static way of doing isotherms as well as the dynamic way of doing isotherms, and combines them into one instrument. In a very easy to use interface, you set the test up, you close it, you walk away, you come back, and your results are generated. It's a standalone instrument, doesn't need any exterior gases. It's all self-contained. You just have to maintain some desiccant and the water tank. So a very good way of being able to investigate these moisture absorption isotherms, which you've been talking about and using through the earlier part of the discussion to actually identify that critical water activity where your product can maintain its optimal shelf life. Now, why would you want to have both instruments? Well, if you have dynamic isotherms, you can find the glass transition or that inflection point that's an indication of stability, where things are changing and you maintain conditions below that, you'll maintain stability. But it doesn't provide any kind of information about how fast things are happening because we're not holding to equilibrium or doing things statically. And so for that, you need a static isotherm. So when you use a static isotherm, you get the kinetics absorption, or you get the kinetic curve, where you can see how much the weight's changed over a certain amount of time. But you also get to see crystallization when you use a static curve that you won't during dynamic if it experiences a glass transition. You don't see the crystallization because it just moves too fast. So there are things to be able to see from the static isotherm, and there are things that can be seen and investigated using the dynamic curve. So ideally, an instrument would have the ability to do both. And again, the Aqualab VSA from Decagon is the only instrument that can do both. It can do dynamic curves, high resolution, shows you inflection points, and then it can, even on one sample, can shift over to a static curve and then show crystallization and kinetics absorption. So all of that's contained in one instrument with our Aqualab VSA, making it a very powerful instrument. And again, the idea here is to bring everything together. So Is it microbial stability that ends shelf life? Then that's certainly related to water activity. But more than likely with a confection product, it's going to be something else that ends shelf life, whether it's chemical stability, moisture migration, texture, etc. Those things have correlations to water activity as well, and it is possible to identify the sweet spot in terms of water activity for any of those particular processes that could end shelf life. How do you go about finding that? Well, so then you got to go in and start investigating using these tools that we've shown in the moisture absorption isotherm curve, hence the need for the Aqualab VSA. Once you've determined where that sweet spot is, then you need to monitor the processing using a water activity to make sure you meet specifications. And so then that uses the benchtop instrument, which is a QA tool. So the VSA is meant to be a research tool, and the water activity meter is meant to be the QA tool that then makes sure that you're meeting the specifications as identified using the tools we've shown and the Aqualab VSA. And then it all comes together by combining these into shelf life models that are useful because they combine both water activity and temperature. So it's our goal always here at Decagon to be able to continue to be the world leaders in water activity measurement, but not just water activity, but complete moisture or all moisture in different types of products, and what those relations and how they can impact how they can impact shelf life. And so we continue to research new areas like the hygrothermal time model, different types of instrumentation, in hopes that we are able to be your most complete source of information about moisture in confection products. And with that, I thank you for this opportunity.